Hi everyone, welcome to this video on segmentation in computer graphics and visualization. Have you ever wondered how your smartphone knows exactly which part of your photo is a face when applying those playful filters? Or how self-driving cars can distinguish between pedestrian, stop sign, and the open road? What about how doctors can precisely locate a tumor in a complex medical scan? The answer lies in a powerful technology called segmentation. Whether you're working with 3D models, rendering scenes, or visualizing complex data sets, segmentation plays a vital role behind the scenes. Let's explore what it is, how it works, and why it matters. Now, before we dive deeper, let's clarify a few terms that often get used interchangeably: segmentation, clustering, and partitioning. While they all involve dividing data, the focus is slightly different. Segmentation groups data based on structure or geometry, for instance, separating the arms, torso, and legs of a 3D model. Clustering, on the other hand, groups elements based on similarity, like color or surface curvature. Partitioning usually refers to dividing space itself, like splitting a virtual world into zones for optimized rendering. Understanding these differences helps us apply the right method for the right purpose. Now let's explore the types of segmentation in computer graphics. Before we move on to 3D segmentation, let's spend a moment on image segmentation, which is all about dividing 2D images into meaningful regions. This is all about This is particularly useful in computer graphics when we need to isolate specific parts of an image, like separating a character from the background or identifying different textures on a surface. It's widely used in areas like texture editing, object recognition, and image-based modeling, where 2D data serves as the starting point for more complex visual tasks. Now let's explore mesh segmentation, one of the most common forms in computer graphics. A mesh is essentially a network of vertices, edges, and faces that form a 3D surface. By segmenting this mesh, we can isolate parts that share similar geometric properties like limbs on a character or individual components of a mechanical object. This is especially useful in animation where different body parts need to move independently, or in 3D printing where separate parts might need to be fabricated individually. Now let's move on to volume segmentation, which deals with 3D voxel grids commonly used in medical and scientific visualization. Imagine a 3D scan of the human body. Volume segmentation helps us isolate organs, tissues, or even anomalies for further study. Techniques like region drawing, thresholding, or the marching cubes algorithm are often used to extract surface and structures from raw voxel data. This is critical in fields like biomedical imaging, fluid simulation, and even geological modeling. Another important application is scene segmentation, especially relevant in rendering virtual environments. Large 3D scenes can be incredibly complex, and rendering everything at once is inefficient. That's where techniques like binary space partitioning of trees and KD come in. They divide the scene into logical sections so only visible or relevant parts are rendered at any time. This dramatically improves performance in games, simulations, and VR experiences. So, what role does segmentation play in visualization overall? Quite a significant one. Segmented data allow us to apply different materials or shaders to different parts, highlight features, and interact with individual components. In immersive environments like augmented or virtual reality, segmentation enables user-guided exploration, helping users focus on areas of interest while hiding irrelevant details. It transforms raw geometry into understandable visual information. Despite its benefit, Segmentation isn't always straightforward. Complex shapes may not have clear boundaries. Too much segmentation can clutter a model, while too little might miss important details. Moreover, different applications may demand different segmentation criteria, making it hard to define one size fits all solution. Balancing accuracy, computational efficiency, and semantic meaning remains an ongoing challenge in this field. To sum up, segmentation in computer graphics and visualization is more than just a technical step. It's a foundational concept that enables us to understand, manipulate, and enhance digital content effectively. From image segmentation in 2D to mesh and volumetric segmentation in 3D, these techniques are vital for modeling, rendering, animation, simulation, and even scientific data interpretation. Segmentation helps reduce complexity, improve processing efficiency, and unlock higher levels of interactivity and realism in virtual environments. As graphical data becomes increasingly detailed and immersive, especially with the rise of technologies like VR, AR, and real-time rendering, the importance of accurate, automated, adaptive segmentation continues to grow. In essence, segmentation is what allows us to convert raw data into meaningful structures, turning pixels, vertices, and voxels into interactive, understandable, and visually rich experience. Thank you.